Justin Talbot is a chemistry student, and Stefan Leboyek is an astrophysicist. So broadly, the motivation for this work is potential of graphene for applications. So Ivan gave an excellent introduction as to what graphene is, so I'll skip many parts of that in my talk. But graphene is a semi-metal, and it sometimes displays properties of dielectric, for example, when the screening of charges is concerned. But in other instances, like in the case of electrical conductivity, it remains a metal. And as a metal, graphene is not really good to make a transistor. So you want to suppress conductivity in some controllable way. One of the ways to do that would, for example, be excuse me, to cover it with hydrogen atoms. And if you cover every carbon site with a hydrogen atom, you'll get something that is called graphene, and it's equally bad because it's a dielectric with a gap of the order of several eV, 5 eV. So you want something in between. And therefore, there is a question of what happens if you have a partially hydrogenated graphene, what those graphene impurities will do. Will they want to aggregate? Will they want to disperse? And so on. So what we were looking at was the effective interaction of hydrogen atoms deposited on the graphene lattice. Graphene is a honeycomb two-dimensional crystal of carbon atoms. Its low-dimensional spectrum is gapless, and the Fermi level sits right in between the two Dirac cones. And in the Brillouin zone, there are two different K points, which ultimately take their origin in two different sublattices of the honeycomb lattice, which, as Ivan pointed out, is actually a sum of two simple triangular Bravais lattices. So if you place two impurities, two add atoms on a graphene crystal, then those add atoms are going to interact with each other. And this interaction can be visualized as a modification of the wave function of conduction electrons by one atom felt by another atom. In itself, this is nothing unusual. It's just like archic Y without spin. And in the usual three-dimensional metal, this would be seen as potential energy oscillating in space, a phenomenon called Friedel oscillations. In 2 dimensions, let me start with a conventional 2-dimensional electron gas with a parabolic spectrum as formed at the interface of two semiconductors. I want to consider a short-range interaction with the interaction strengths being a parameter. And in case of a parabolic spectrum, I can construct a dimensionless strength of this impurity by multiplying it to the effective mass of this parabolic spectrum and divided by h bar squared, which I set equal to 1. If that product is much less than 1, then you are in the limit of a weak impurity, and you can treat it using the first Born approximation. Then modification of the wave functions is linear in the potential strengths. And then the second atom probes those wave functions with additional interaction strength. So you get the effect to the second order. In graphene, so at least you have a regime where the impurity is weak. In graphene, the situation is different. There is no mass. You only have Dirac velocity. And so to construct a dimensionless parameter, you must use something with a dimension of the length. So this is a characteristic length that you have in your problem. It's a distance at which you are probing the change of the wave functions. But otherwise, it's just a replacement of the mass with this effective mass, and you get additional power of the distance, but otherwise it's pretty much the same. So it decays faster, but oscillates with the same with the same wavelengths. You can visualize this faster decay as the suppression of backscattering that chiral electrons have on the Dirac cone. Or you can view it as sort of a quantum interference between two sublattices. So along each sublattice, the propagation is more or less conventional, but the two sublattices interfere destructively, and so you have a smallness, another smallness, which gives another power of r. Just like Ivan explained, if you now go from continuum model to a lattice model where you place, let's say, potential, like a substitution atom on two different sites, the interaction energy will depend on whether the add atoms, so impurities, reside on the same sublattice or on opposite sublattices. If you just perform perturbative calculation, you'll get same power, but in one case it will be attractive. That's where two atoms sit on the same sublattice. In the opposite case of different sublattice, the interaction will be repulsive, but it will be numerically a bit stronger. So if you average over the positions of A and B atoms in the continuum limit, you will get what effective Dirac theory predicts. But you can do that using the lattice calculations. Now, the interesting thing happens in the opposite limit. So in graphene, there is no dimensionless parameter, so everything depends on the distances at which you are going to look at your problem. And if the distance is very small, you are going to get a strong coupling limit for any strength of the impurity, in principle. That might never happen, of course, because the distance required might be less than the lattice spacing, but at least in the effective model, you always have this problem of a strong impurity. So it makes sense to ask what happens to the interaction energy when the impurity strength is very large. And that's what was addressed first by Shitov, Abanin, and Levitov in their 2009 paper. And these are the results. So the first result is that the interaction becomes long range. So instead of 1/r cube dependence, now you have almost Coulomb type of interaction of short range impurities. Well, and also, albeit suppressed by the logarithms. In case of same sublattices, there are two logarithms, but in case of opposite sublattices, there is only one logarithm. Also, notably, the sign of the interaction reverses. So now it's attraction for opposite sublattices and repulsion for same sublattices. They also looked at ensemble of add atoms thrown on carbon sheet, and they calculated energy per impurity in the limit of very strong impurity. So potential realizations are, again, strong substitution atom, which is almost impossible to realize, a vacancy, or a resonant Anderson impurity. And that is, hydrogen is one of the candidates for that, because it has a resonant level which is not very far from the Dirac point. How far, it's a subject of debate, and different calculations give different results. So we started working on this problem by first reproducing the results of Shitov, Abanin, and Levitov, and we mostly agreed with their results with one exception. So there is a lot of, in principle, there is difference whether you dope your system, whether you put impurities on your system at a fixed chemical potential, which is then pinned at the Dirac point, versus fixed number of conduction electrons. So it's a contacted sample versus isolated sample. So what they found was that the interaction energy pretty much doesn't depend on whether you have canonical ensemble or grand canonical ensemble. The numerical calculations that we did not agree with that. So what we saw was pretty much the same attraction strong attraction from opposite sublattice impurities, which wins in case when you see that there is just a single logarithm here, but the double logarithm squared there. So on average, attraction wins, and that's what they found. What we found, surprisingly, was that while this is indeed the case for grand canonical ensemble, for a fixed number of electrons, we got repulsion. We got a totally different sign of the interaction. So we started looking at their calculations, and we realized that while in the opposite sublattice case, this term is pretty much what you have, in the opposite sublattices case, this 1/log term is just the beginning of an expansion. And the next order term is very similar to what you get for same sublattice case, except the sign is also positive. However, what we found was that this term disappears if you move away from the Dirac point. So this is a transparent. This is a slide just in case somebody asks how we calculated that. But since nobody is asking, I'll just move to the next slide. So let me explain the physics behind strong impurity case. So when the strength of impurity increases, you have to take into account multiple scattering from the same impurity. So conduction electrons come back to the same impurity many times. So you have to sum the entire geometric series, and you get this so-called T matrix, which with a denominator that depends on the strengths. But when the strength of the impurity goes to infinity, you get so-called unitary limit. And the T matrix, the scattering strength, just depends on the spectrum of the system, on the Green's function at coinciding points. So in graphene, this Green's function has logarithmic dependence on energy, and it's also proportional to the energy itself. Now, this dependence is not as much reflection on graphene itself. It's just a consequence of 2 dimensions and the fact that the chemical potential is at 0 point. Then the relevant energies are defined in terms of the characteristic length scale of the problem. So you have to replace energy with 1 over the distance. And then what you find is that at small energies, at low energies, you get a distance-dependent effective strength, which you can then use in the same second order Born or lowest order Born approximation just to reproduce their result. So you get 1 over logarithm squared. And that's pretty much what you have in the strong coupling limit in case of impurities sitting on the same sublattice. The problem is that when you try to explain the same with the same qualitative arguments the opposite sublattice case, you cannot do that. You can explain this second subleading term, but the leading term apparently is non-analytic in this new renormalized effective strengths. So what we found eventually, these 2 problems that we spotted, one is that the interaction strength, the interaction sign of interaction changes from one ensemble to the other ensemble, and this non-analyticity of the leading interaction correction have the same origin. And this origin can be elucidated if you just solve a 2-impurity problem in the lattice model. So you start with a tight binding Hamiltonian, and then you add 2 potential impurities. So again, the strength of the impurity is then going to be taken very large. But this problem is solvable. You can solve 1 impurity, you can solve 2 impurities, you cannot solve arbitrarily many impurities, but for 2 impurities, the problem allows a solution. So to understand what's happening, again, look at the T matrix for a single impurity. And that T matrix has a singularity. That singularity indicates a formation of a quasi-bound state. And for a strong impurity, that quasi-bound state is sitting very close to the Dirac point. And in the limit, in the unitary limit, it just pins to the Dirac point. Now, of course, if you have 2 impurities, those quasi-bound states begin to interact and form something else. So by the way, if you have any questions, just interrupt me at any time. We have plenty of time, right? Nobody is going to this excursion, right? In case when you have 2 impurities, everything depends on, again, whether you have same sublattice or opposite sublattice case. In the same sublattice case, the splitting is roughly of the order of the energy level itself. And most importantly, no energy level is ever pushed through the Dirac point. In the opposite sublattice case, completely different picture happens. At some threshold strengths, one of the levels is pushed through the Dirac point. And in the limit of very strong impurity, that energy turns out to be exactly the energy that corresponds to that leading term. So that leading term is just energy of that bound state, and that energy is only found in the opposite sublattice case. So I can visualize those 2 terms that I explained to you before. One, the leading correction as the energy of a bound state, which brings most of the energy. And then the second order term, this is just renormalization of the band electron energies. So it's present in both cases, in AB and BA case, and it has the same sign. But the difference is in the additional bound state that you find here. So this explains why you get different effective interaction energy for the ensembles of particles when you have fixed N versus fixed chemical potential. If you have fixed chemical potential, then you populate all the lower energies, and with the distance between impurities, those levels move, and you get attraction. However, if you raise chemical potential above the upper level, or you move it below the lower level, either both states are occupied or both states are empty, and the energies add to 0, and the effect of this bound state completely disappears. So in case of many impurities, we also perform numerical calculations by taking 42 by 84 sample of graphene and just diagonalizing Hamiltonian and then calculating energies. So this is our numerical result. For grand canonical ensemble, you get attraction. For canonical ensemble with a fixed number of electrons, you get much weaker but repulsion. So this can be explained by the following diagram. Among different atoms, you get pairings AA or AB. And they form this AA band, which is clearly visible in the numerical calculation in the density of states. And then in addition, you get those AB states. And some of those states are pushed across the Fermi level through the Dirac point. So you get more states in the upper cone than states in the lower cone. So again, if you change the sign of the interaction, the picture will reverse. So when you populate only lower states, as in grand canonical ensemble, you just harvest your bound states, all of them, and you get strong attraction. However, if you have a canonical ensemble, you have to populate n states. So you have to, the chemical potential is somewhere here. So you start populating both band states and those quasi-localized states. No one knows the exact order in which they are populated. It's sort of a competition. So the mean level spacing of the quasi-band states is logarithmically lower, smaller than the mean level spacing of the band states. But at about 1 electron per site, at about where you have canonical ensemble, finally you populate enough those upper states to negate the effect of attraction so that the repulsion due to band electrons wins. So yeah, that's pretty much the punchline of my talk. The second part is, I'll just briefly say a few words about it. What implications does it have on transport of hydrogen atoms? So you might want to ask, what use is this for? Well, in some way, it's pretty exciting because by simply changing the chemical potential a little bit, you are able to go from attraction to repulsion, and so potentially you will be able to go from aggregation to dispersion. But the question is of the mobility of hydrogen atoms. How easily do they respond to that change of energy? And so you have to calculate the hopping probability. And for a single hydrogen atom, it's just some chemistry, tight binding, and you end up with the bandwidths of order of 1 microelectron volt, which corresponds to like centimeter per second, which is still huge on a macroscopic scale. But in addition, you have this effect. If you have just a single hydrogen atom hopping, it's just elastic hopping. But suppose you bring another hydrogen atom, which then modifies the energy of the first hydrogen atom. Or, yeah, let me talk about hydrogen atoms now. And so that the energy changes very much. So the characteristic energy of that interaction that I was talking about is roughly tens of eV. So the tunneling becomes inelastic. With that width of the band, you have to invoke other sources of energy to make this hopping possible. And two things that we looked at were phonon-assisted hopping with flexural phonons and electron hole pair assisted hopping. So I will skip the calculations and discussion of that so that we can go to a much nicer entertainment. But the result is that the eventual hopping probability is rather small. So we estimated it to be one hop per second for temperature of the order of the room temperature. Thank you for your attention.